this work is a cooperation with the FFT Institute at the University of Kassel. On this slide you see the content. I will start with the introduction, then say some words to the object of investigation. After this, something to the used methods. Then I came to the results, and I will end my presentation with a conclusion. Adhesive joints are well used, very important and established in many industries, automotive, aerospace, and so on. And during the manufacturing process of these joints, different effects can occur. Here you see some examples: porosity, cracks, curing errors, attachment, the so-called kissing bonds, and defect and voids. And all these leads to a loss of structural integrity in the entire structure and reduce the mechanical performance of the joint. And our general aim is to answer the question how we can use the energy release rate and the traction separation law in presence of voids. But first we'll have a closer look to different measurement methods and how we can localize voids. For this we performed double cantilever beam test. The specimens you see on the bottom of the slide. We used the Sikaflex 521, that's a soft rubber-like adhesive. And for the joint thickness we choose 3 millimeters, and we prepared specimens without voids and with voids, and a width of 40 millimeters. On this position you see here on the bottom. We measured the J integral, and we choose different 3 optical measurement methods to measure the adherence deformation, and these are the sherography system, then backface grain measurement with optical fibers, and the digital image correlation. On this slide, on the picture, you see the test setup. In the middle of the specimen, front there are rotary encoders, and below load cells. That is for calculate the J integral. In the end of the specimen, you see the optical fiber and inclinometers to calculate the end beams rotation. In front of the picture, there's the DIC sensor. We have 2 of this for 3D measurement. Additional lighting, and below there is the sherography system. With this we measure the deformation on the lower surface of the adherence. We perform all 3 measurements simultaneously. Now some words to the test procedure. The test was performed displacement controlled. We started with constant displacement rate. After this we hold the position for 5 seconds, then we load again. In the middle you see here a larger area to hold a longer time period to hold the position. This is caused by the saving the data from the sherography system, and then we can start again loading. Now some words to this plateaus. This is caused by the sherography system. I think you will later more. Also on this, during this hold position, relaxation occurs. That's on the one hand a problem for the J integral measurement, but a benefit for the sherography measurement. Okay, now the measurement methods. I will start with the sherography. This is commonly used for qualitative tasks. For example, you have plates of composite materials, and you can detect the positions of delamination. And we try to use it as quantitative measurement. During this measurement, we take 5 pictures for first to calculate first state, then we take 5 pictures to calculate the second state, and difference of these 2 states leads to the so-called shallow bump. You see a picture here, example. there's some phase shifts. This is example for a circular plate loaded in the middle. Then we can demodulate these pictures. We reduce the phase shift, and this leads to this surface, and this delivers us a component of the linearized deformation gradient. Now, back face strain measurement, the name. We measure the strain on the back face and the adherence. Therefore, we use the optical fiber. We bond it here like the red dotted line. As device, we had something from Lunar Innovations, and with the system, we are able to measure the strain every 0.65 millimeters in the fiber. For this measurement system, or for this method, the device sent light of different wavelengths in the fiber. Here I took a piece out. There the light is reflected, and our device calculated the intensity with respect to the light frequency. I hope you see it in the gray line here. And after deformation of the fiber, this measurement is again, and we got the red line, and the shift of these two lines is proportional to the fiber strain, and when we have a temperature low to the temperature. The last measurement method is, I think, the well-known digital image correlation. We have two camera sensors, one on the left, one on the right, with a fixed distance and a fixed angle, and so we can calculate every point's position on the specimen, and also the displacement of these points, and we use it to calculate the deflection curve of our adherent. Therefore, we used the big 3D8 software from Correlate Solutions. The software evaluated the displacement of the points on this line, the top and the bottom. Now the evaluation method, we assume for the adherence that we have a Euler-Bernoulli beam theory, and we expect of the void's position a constant transverse force, or this third derivative of the deflection curve is constant. For the digital image correlation, our acquired data is the deflection curve W of X. We have to differentiate 3 times to get the third derivative or the transverse force. The backface strain measurement is easier. Our acquired data is epsilon, the fiber strain, and with the distance from the neutral axis to the marginal fiber C, we can calculate curvature, and the curvature is proportional to the bending moment. We have to differentiate this once and get the transverse force. Now the results, first of the backface strain measurement. In this diagram you see the second derivative of the deflection curve plotted over fiber position. This is proportional to the bending moment and our fiber strain. In the middle, the dotted line is the crack tip, the initial crack tip of the adhesive layer. In front is the clamping. That's the example for the specimen without void. And then we differentiate this once, and now we're searching for a constant value, this curves. There is something in the front, but that's the lever arms of our specimen. That's no void. And in the area of the adhesive behind our crack tip, there's only a decrease and an increase and no constant value. This is the reference, and on the right side you see the same diagrams for the specimen with void. You see the values for the second derivative is smaller, and below you see third derivative of these, and in the middle, where's the position of the void, you can see their constant values. I think that's matched very well. Now, results for the DIC measurement. Here on the top you see the deflection curve, W, plotted over the position. Here in front, the dotted line shows also the crack tip. And here we have to differentiate 3 times. And this differentiation leads to increase of the numerical noise. It's not so easy. You also see here no constant value. You see can on the okay. So on the left side, you see the results for specimen with void. Also the deflection curve, you see it's much higher. And on the bottom, the third derivative, and you see it fits also good with the position of the void. And I forget, the blue is the beginning of the test and the red lines are the end of the test. Now results of the sherography measurement. On the top you see for the specimen without void, the sherogram with these phase shifts, and below the demodulated sherogram, and you see it's very smooth and is like we expected from the deflection curve. Now the interesting part, the voids, the specimen with voids with 40 millimeters. The sherogram looks slightly different, and in the middle where the void is, you can see there's something unexpected. That's the void, and the progression of this is not matching very well with our expectation from the deflection. So pleased. The measurement of the J integral, we calculated like the formula on the left, and we calculated like we have no void. But the normal line is without void, and you can see for the specimen with void, the energy release rate is smaller. Now I will end with the conclusion. For the DSC result, we can locate the void, but we can't measure the size of the void, and it's different because we have large sensitivity to the numerical differentiation. The sherography is quite good to locate the position of the void, but not the size. And specimen without void shows the values like we expected from the bending, from the deflection curve. But one disadvantage is that it's not usable for continuous measurements. We have to calculate take 5 pictures at one state with a rate of 9 Hertz, and then we have to wait and take the next pictures. The backphase strain measurement shows the comparatively best results. We can detect the void's position and also the void. Now some words to the future work. With this measurement, measurement methods, we want to calculate the deformation field of the adherent, and with this, with the backphase strain measurement, I think we're able to calculate the strain in the adhesive layer for this one-dimensional problem, and we can evaluate the energy release rate, and I hope we answer the question how we can use the fracture energy in presence of defects. Thank you for your attention, and feel free to ask.
Just time for a quick question. Anyone?
When you're doing the 3 differentiations? Do you apply some kind of smoothing on the initial data, or?
Yeah, I smooth the data before the differentiation, and I have to smooth 3 times, and it's not easy.
Yeah.
And the values or the parameters of the smoothing have a effect.
A major effect.
Yeah, that's a good point. I forget to say it, but we can detect a void when we know where is the void. And then we can use the parameters, but we have to have a closer look on this parameter.
Thank you.
I didn't understand. You have a mode 1 loading, yeah?
Yeah.
But it's not cracking, you know, it's just you pull on that and then it's deforming. Why do you have bending in the adhered parts? You know, if I pull here, then it should be unlocked. Or
No, we have
maybe I didn't see the.
we have bending.
If you go back to the sketch, maybe. No.
This.
Yeah, the sketch on top.
This
Yeah,
is
why do you have a bending moment on the right hand side?
on this side.
Yeah.
We have a force on this.
Yeah, and the force down the other side.
Yeah, but we have this adhesive is rubber-like, very soft.
Okay.
We have a
yeah.
low modulus, and the process zone is very
So
large.
it's the adhesive, there is a tension on that, and
Yeah,
that
we
where
have-
it deforms and then,
Yeah.
okay. But then you said your shear load is constant, your third derivative is constant.
In the place where
Look at this distributed
Yeah,
force,
yeah.
no?
so here, in the part where the void is.
Oh, okay. But this would mean that the void is going with the whole width.
There's this void is predefined, and we have transfer force in this region where the adhesive is,
Yeah.
and then we have the void, and we expect that there is no transverse force because we have no line load.
Yeah, this
From-
is clear, but I understand.
Yeah.
But this is a 2D problem, yeah?
Yeah.
But you would this is not a void, I mean, this is a denomination over the whole width.
Yes, it's very large.
Yeah.
We use this, we do tests before, and we saw that voids of 10 millimeters we cannot localize, and we choose this void.
Yeah, it's actually interesting, your question, because you see there on the sociography, it gives you deformation immediately. So it's the derivative of the displacement field. And there you see exactly it's 0. So it's not actually giving you any deformation at every. Yeah, it's interesting.
Thank you.
Thank you again.